Let's look at transformers. No, they are not the fun toys, but they are things that we use all the time. They're very useful devices. Here is what a transformer looks like. There is this iron core, and on one side of it there are windings of wire. On the other side there are a different number of windings, and in these wires there is a current. So we call this the primary. So there's a primary voltage across here, and there is a primary number of turns. Then we have the secondary over here. There is no current going through it originally, and it has a number of turns n sub s. Now, there is a magnetic flux through here, and that magnetic flux is the same for both the primary and the secondary. So the EMF of the primary is the negative number of turns in the primary times the magnetic flux change with respect to time. So this is Faraday's law. Well, the same kind of thing applies for the secondary, where we have the EMF in the secondary is the negative number of turns in the secondary times the change of magnetic flux through the secondary as a function of time. But since delta phi delta t is the same for both of these equations, that means that E sub p, the EMF in the primary divided by the number of turns in the primary, equals the EMF in the secondary divided by the number of turns in the secondary. So we have that over here. Then we can rearrange this so that we have the EMF in the secondary divided by the EMF in the primary is number of turns in the secondary divided by the number of turns in the primary. So there is a relationship between the secondary and the primary of the EMFs and the number of turns. Now, since we can neglect the resistance in the coils, then we can say that the terminal potential, the terminal voltage in the secondary divided by the terminal voltage in the primary is number of turns in the secondary divided by the number of turns in the primary. So based on that, if the number of turns in the secondary is larger than the number of turns in the primary, so if we have more turns here, then the voltage in the secondary will be higher than the voltage in the primary, and we'll call it a step-up transformer. But if the number of turns in the secondary is smaller than the number of turns in the primary, which is what we have here, so the primary clearly has more turns than the secondary, then the voltage in the secondary over here is going to be less than the voltage in the primary, and we have a step-down transformer. Now, if we apply conservation of energy, we realize that the amount of energy that the primary supplies is going to be the same as the energy in the secondary. That also means that the rate of change of energy in the primary equals the rate of change of energy in the secondary. So that means that the average power in the primary equals the average power in the secondary. So if we write average power as current times voltage, then we have current in the primary times voltage in the primary equals current in the secondary times voltage in the secondary. So we rewrite this, so we have the currents on one side and the voltages on the other side, and then we have current in the primary divided by the current in the secondary is voltage in the secondary divided by voltage in the primary. So if we say that voltage in the secondary divided by voltage in the primary is number of turns in the secondary divided by the number of turns in the primary, then we have this relationship between the ratio of the currents and the ratio of the number of turns. So then we have current in the primary divided by the current in the secondary is number of turns in the secondary divided by the number of turns in the primary. So while we have step-up transformer, we're stepping up the voltage, we're going to step down the current and the other way around. When we're stepping down the voltage, the current is going to be stepped up. Now, why did I say that these are useful devices and we use them all the time? Well, because when we're charging our phones, we use this plug that goes into the wall. And that plug, it has some circuitry inside it, and it converts from the 110 volts that comes out of the wall socket to a voltage between 3 and 9 volts, depending on what phone we have and how much voltage it needs to charge the battery. So those are transformers. We use transformers in so many different things, so many electronic devices, electric devices, that don't necessarily operate at 110 volts, but they all come with cables that have these little transformers at the end, and they convert the current and the voltage into what the devices need to charge or to operate. So that's why transformers are very, very useful.